Okay, so now let's start to solve problems relating to Otto cycle. Okay, so the first step that we need to consider is that we are given the certain values. So we have K, which is 1.34, corresponds to hot air properties. Next, we have pressure, that is P1, is equal to 101.3, so that is in kilopascal. Next, we have volume, V sub 1, which is 0.038 cubic meters. And we have temperature, so that is T sub 1, which is 32 degrees Celsius. So if we convert that in terms of absolute temperature, we just add 273, so that is 305.15. So that is in Kelvin. Next, so since we know that the gas is air, so let's write the specific gas constant of air. So since we are dealing with SI units, this is 287.08 joules per kilogram Kelvin. Okay, so we are asked to solve for V2 or volume 2, P2, P2, P3, P3, P4, P4 or pressure 4. So basically all the pressure, volumes, and temperature of the cycle, the heat rejected, the work net, efficiency, and the mean effective pressure. Okay? So upon observation here, we are given as well clearance, right? So the clearance ratio, or the clearance, is 10%, or simply 0.1, and heat added, QA, which is 12.6 kilojoules. Okay? So by observation, we can immediately solve for, we are given P1, V1, and T sub 1. So P, V, and T are already given, and we have R. So immediately we can solve for the mass of the substance, which is given by P1 V1 over R T sub 1. So what is P1? That is 101.3 kilopascal, that is in Newton meter squared, times V sub 1, that is 0.038 cubic meters, over R, which is 287.08 joules, that is Newton meter kilogram Kelvin, times T sub 1, that is 305.15 Kelvin. So if you perform dimensional analysis, Newton will cancel out, kilogram, not kilogram, so it should be Kelvin, kilogram will retain, and meter squared, meter cube, and meter will cancel out, leaving us with kilograms. Okay, so if we plug it in our calculator, we will have, so that is 101.3 kilo times 0.038 divided by 287.08 times 305.15 equals, so we have the mass of 0.0439 kilograms. Okay, next, the next thing upon observation that we can solve is that we can solve for the compression ratio. Since we are given clearance, so compression ratio can be solved as a function of the clearance, which is 1 plus C over C. So this one is 1 plus 0.1 over 0.1. So this one, 1 plus 0.1, that is 1.1 divided by 0.1, that is roughly 11. So let's double check. So we have 1 plus 0.1 divided by 0.1, so that is 11. Okay, so we have the compression ratio of 11. Next, we are asked to solve, so let's proceed with letter A. We are asked to solve for V sub 2. Okay? So we know that the compression ratio is also equal to your V1 over V2. Okay? So therefore, V2 is V1 divided by your compression ratio. Okay? Wherein V1 is given by 0.038 cubic meters over 11. So before we solve this one, I would like you to inspect your PV diagram. So what are we going to expect with V sub 2? So from V sub 1 to V sub 2, what happened to your volume? So it drastically decreases. Okay, so from higher value, it ended up with a lower value. So once you've solved a value that is greater than your V sub 1, therefore you need to repeat the process. Okay, so here we have 0.038 divided by 11. We have 0.00, so that is 345 cubic meters. Okay, so as you can see, the number of zeros with V sub 2 is greater, therefore it consists of a very small quantity. Okay, so this is your V sub 2. So that is letter A. Next, we are asked to solve for V sub 2. Okay, so right now from point 1, so we are done with point 1. We have P1, V1, and T1. So point 1 is already checked. So let's put a circle around that. So this one is already finished. Okay, so let's just put the check in point 1. So from point 1, we need to relate point 1 with point 2. So as we've mentioned, this one is an isentropic process. Okay, so therefore we need to use isentropic relation in solving for T sub 2. That is T sub 2 over T sub 1 is equal to V1 over V2 raised to K minus 1. Isolating T sub 2, we have P2 is equal to T sub 1, that is 305.15 times V1 over V2. So V1 over V2 is our compression ratio, so therefore we can substitute compression ratio. And K is our hot air property, that is 1.34 minus 1. Okay, so before solving this one, check again your TS curve. Okay, so from temperature 1, what do you expect at temperature 2? So therefore, we expect that temperature 2 is relatively higher compared to temperature 1. So otherwise, let's say you compute a value less than 305.15, immediately your answer is incorrect. Okay, so let's try to solve that. So that is 305.15 times 11 raised to 1.34 minus 1. So we have 689.583. So that is in Kelvin. Okay, so let's try to perform a quick hypothesis. Okay, so how are we going to generate a quick hypothesis? So since we have the compression ratio, we can solve for letter J immediately. Okay, but we will prove it later on if our answer will correspond to the same efficiency, because we know that in an Otto cycle, the efficiency is given by 1 over RK raised to K minus 1. So the efficiency here is 1 minus 1 over 11 raised to RK, that is 1.34 minus 1. So therefore, the efficiency here is given by, so that is 1 minus 1 over 11 raised to 1.34 minus 1. So that is 0.5574. 5574, or approximately 55.74%. So we will try to prove this one, okay, using the conventional approach. So letter C. So letter C, we are asked to solve for P sub 2. So P2, so that is also an isentropic relation because point 2 or pressure 2 is located here, okay? So P sub 2 is equal to, over P sub 1 is equal to, that is V1 over V2 raised to K, wherein P2 is equal to P1 raised to V1 over V2 raised to K. Okay? So, let's write it here. So, P2, what is the magnitude of P sub 1? 101.3. So, that is in kilopascal times V1 over V2, that is our compression ratio, raised to 1.34. So P sub 2, is equal to 101.3. So that is kilo times 11 raised to 1.34 equals, so this is 2051. So let's place it using kilo. So that is 2,518.115 kilo. So that is in kilo pascal. Okay, so this is your P sub 2. Next, so now we have P sub 2. P sub 2, what we don't have is V sub 3. Okay, but we know in our PV diagram, V2, so may V2 na tayo dito, right? V2 is letter A. V2 is equal to, as you can see in the PV diagram, V2 is equal to V sub 3. And V sub 1 and is equal to V sub 4 by simply looking at your PV diagram. So 2 and 3 are represented by a straight vertical line. So thus with 1 and 4. Okay? Next. So now we have this certain magnitude. We can proceed with T3. So that is letter D. Okay? So for letter D, we are asked to solve for T sub 3. Okay? So actually, we can use, so since that is, we are relating already point 3 and point 2. So actually, you can use P2 V2 T2 is equal to P3 V3 T3. So this is a constant volume. You will have P2 T2 equals to P3 T3. However, you don't have yet P sub 3. So therefore, you cannot use that because you have two unknowns in a single equation. So what we are going to do here is that, but actually you can use that. Let's say there is the given is already representing T sub 3 or the highest temperature of your cycle. You can use combined gas law already. But in this case, we don't have one. But what we have is that we are given heat addition, which is at this part. Okay, this is heat addition. So therefore, we can conclude here that QA, or the heat addition, is equal to mCV. So that is within the limits of T3 minus T2. So if we can solve for T sub 3 here, what we're going to do is just divide both sides by mCV and transpose T sub 2. Sorry. So, transpose T sub 2 on the other side of the equation. You will have T sub 3 is equal to QA over MCV plus T sub 2. Okay? So, QA is given by 12.6 kilojoules. So, joules is in Newton meter. So, let's double check. 12.6 kilojoule divided by the mass, which is 0.0439 kilograms, times CV. We don't have CV yet, but we can solve that using CV is equal to R over K minus 1, wherein R is 287.08 divided by K, that is 1.34 minus 1. So CV is equal to, so that is 287.08 divided by 1.34 minus 1. So we have 844.352. So that is in joules per kilogram Kelvin. So let's plug it in our equation. We will have 844.352. So that is joules Newton meter kilogram Kelvin plus T sub 2, that is 689.583. Okay, so this is in Kelvin. So cancel everything. We will have T sub 3 is equal to, so let's plug it in our calculator. So we have 12.6 kilo divided by 0.0439 times 844.352 plus 689.583. Okay? So we will have 1029.507. So that is in Kelvin. So as you can see, T3, if we look back again in your PV and TS curve, T3 is the highest temperature of your entire cycle. Okay? So once you are solving this one, it should be in accordance with that. T2 cannot be higher compared to T3 because it will completely violate the TS diagram of an Otto cycle. Okay? So now we have T3. We are asked to solve for P3. Okay? So this is letter D. So we are going for letter E. So we are asked to solve for P sub 3. So actually, we can use two approaches. One is we can use the one that I've mentioned earlier, combined gas law. And then so this should be 2 first. And then P3, V3, T3. So volume will cancel out since this is a constant volume process. So by performing separation of variables, I can conclude that P3, so cross multiply T3 on the other side. That is T3 over T2 quantity P2. Okay? So T3, that is 1029.507 Kelvin over T sub 2. So T sub 2, that is 689.583. That is Kelvin as well. Times T sub 2. T sub 2 is 2518.115. So that is kilopascal. So as you can see, Kelvin, cancel. So leaving us with P sub 3 is equal to, so this one is 1029.507 divided by 689.583. So times 2518.115 times 10 to the third. So press ENG. This will be 3759.39. So that is kilopascal. So this is the first approach, okay, or the approach that we can use for P sub 3. Okay, next, what about in point number 4? So we have P3, T3, and then we already concluded that volume 2. So let's put a box around here. So we've already concluded that volume 2 is equal to volume 3. So all the volumes, we've already obtained the values of such. So let's proceed with point 4. Okay, so we are asked to solve for T4. Okay, so T4, we can use isentropic relation. So we came from point 3. We came from here. Okay, so we are going downward. So we need to relate point 3 and point 4. So that is an isentropic relation. So letter F. So letter F is simply T sub 4. So we can solve for that using T4 over T3 is equal to V3 over V4 raised to K minus 1. But we've concluded before or earlier that V2 is equal to V3 and V1 is equal to V4. So where did that came from? So it came from this one, or your PV diagram. So V1 is equal to V4, V2 is equal to V3. Okay, so if we substitute this one, we will have T4 over T3 is equal to, we said that V3 is equal to V2 over V4 is equal to V1 raised to K minus 1. So as you can see, this one, V2 over V1, so we have the compression ratio that is represented by V1 over V2. So therefore, this term, T4, we can solve that using T3 quantity. That is simply the reciprocal of your compression ratio raised to K minus 1. Okay, so T4 is equal to T3. So what is our T3? So 1029.507 so 1029.507 times 1 over 11 raised to 1.34 minus 1. So T sub 4 is equal to, so as you can see here, from point 3 or T3, what will happen to temperature 4? So from point 3, your temperature will decrease. Okay? So therefore, we need a value that is less than 1029. So that is 1029.507 quantity 1 over 11 raised to 1.34 minus 1. So we have a temperature of 455.57 Kelvin, which is relatively less than your T sub 3. Okay? Next. So we are asked as well in letter G to locate letter G. Locate your pressure 4, which is also an isentropic relation, which is P4 over P3 is equal to V3 is equal to V4 raised to K. So P sub 4, so we've said V3 is equal to V2 and V1 is equal to V4. Okay? So by performing that as well, we know that P4 is equal to P3 quantity. V3 is V2 over V1 raised to K. And this one as well is also equivalent to 1 over RK raised to K. Okay? So now, let's substitute everything. P4 is equal to P3, that is 3,759.39 kilopascal. So, kilopascal times 1 over 11 raised to 1.34. So, P sub 4 is equal to, so this one is 3,759.39 times 10 to the third. So quantity 1 over 11 raised to 1.34. So this one is 151.234. So that is kilopascal. Okay? So as you can see here, so based on our PV diagram, so point 3 or pressure 3 to pressure 4, it drastically decreases. So therefore, it satisfies the condition. So from 3,759 kilopascal, it decreases to 151.234 kilopascal. Okay? So now we have pressure, volume, temperature of all the corners of the cycle. So the next condition that is asked to us is to compute for the heat rejected. Okay? So that is letter H. So upon the previous video, we know that heat rejected is M or negative M CV T4 minus T1. Okay? So let's try the two equations. Okay? So we have the mass, which is 0.0439 kilograms times CV, that is 844.352. That is in joules per kilogram Kelvin, times T4. T4, that is 455.57 minus T sub 1, that is 305.15. So that is in Kelvin as well. So as you can see here, QR is equal to, so we have negative quantity of 0.0439 times 844.352 times 455.57 minus 305.50. So let's verify. So 305.15. Okay? So since the given is in terms of kilojoules, wherein our heat added, so our heat added is in terms of kilojoules, we must express this one in terms of kilojoules as well. So we have negative 5.575 kilojoule. Okay? So that is our heat rejected. Next. So actually, if you use the other equation, which is QR is equal to MCV T1 minus T4, eventually we'll end up the same magnitude. So let's try that. So we'll have 0.0439 times 844.352 times 455.57 minus 305.15. So QR So as you can see here in the last term, so this one should be inversed. Sorry. This should be 305.15 and 455.57. So as you can see, the difference of these two, if you subtract them, it will correspond to a negative value. So if we try to solve that, we will have 0.0439 times 844.352 times 305.15 minus 455.57. So eventually you will have the same magnitude, which is negative 5.575 kilojoule. Okay, so it will be the same regardless of the type of equation that you've used. Okay, now once we have obtained the heat rejected, we are asked to solve for the work net. So that is letter I. So the work net is given by QA minus the absolute value of QR. QA is given by 12.6 kilojoule. So that is times 10 to the third kilojoule minus the absolute value of this one, that is 5.575, so kilojoules as well. So therefore the work net is equal to, that is 12.6 kilojoules minus 5.575 kilojoule is equal to, that is 7.025 kilojoules. Okay, next, so now we have the work net. Let's try to verify the efficiency, that is letter J. Okay, using the conventional equation for efficiency, that is efficiency is work net over QA. Work net is 7.025 kilojoule over, that is 12.6 kilojoules. So kilojoules will cancel, leaving us with the efficiency, that is 7.025 divided by 12.6 kilojoule. So that is 0.5575, or approximately 55.75% of efficiency. So let's try to verify it with the answer that we had earlier using the simplified equation, that is so 0.5574 or 0.5575. So they have pretty close of a magnitude. So therefore our efficiency from the get-go is correct. Okay, next we are asked to solve for the MEP, or the mean effective pressure. Okay, that is letter K. So we are asked to solve for the mean effective pressure, that is work net over volume displacement. So the volume displacement simply corresponds to the ratio between the largest volume, or V1, so minus V sub 2. Okay, basically the displacement, or the distance between your bottom dead center and the top dead center. So that is, we can write it as work net is equal to V1 minus V2. Okay? So the MEP, or mean effective pressure, is equal to work net, that is 7.025 kilojoules, joules, that is Newton meter, over V sub 1, that is 0.038 cubic meters, minus V sub 2, which is relatively smaller than V sub 1. V sub 2, that is 0.00345. 0.00345 cubic meters. So as you can see, meters will cancel out here, leaving us with 2 on the denominator. So Newton meter squared, so that is Pascal. So our mean effective pressure is equal to, that is 7.025 kilo divided by 0.038 minus 0.00345 equals, so in terms of kilopascals, this is 203.328. So that is kilo Pascal. Okay? So we've already solved for the entire process. So my tip when you are solving Otto cycle or other gas cycles, always check your answers with respect to the PV and TS diagram. Okay? So if the PV diagram says that from point 1 to point 2 it will increase, therefore your answer should also increase, not the other way around. Okay? So I hope you learned something with regards to Otto cycle. So if you have questions and inquiries for the problem, so you can comment it, and then we'll address it immediately for the next video.